Hello and welcome to the lab, Rotational Inertia of Different Objects. Now, from a setup standpoint, as you can see, we have a number of things that go into this experiment. We have a support base with a rod, which will suspend an acceleration sensor. Now, the acceleration sensor in turn is going to be attached to two different objects, which we will which we'll be looking at their moments of inertia of. So this is called a super pulley. It's going to be attached to the top, and we'll need to determine the moment of inertia of this. We also have a hoop that has different interior and exterior radii. Now, in your lab, you'll see the equation for the moment of inertia of this, which we'll discuss subsequently. But to be warned, if you take a look at these objects, they aren't uniform. Okay, so you'll be doing two runs. You'll be doing one run with the pulley here to determine this moment of inertia, and then you'll do the composite object like this. Now that said, in order to get this to actually turn so we can determine its moment of inertia, we have a pulley set up here that will attach to the rotational motion sensor. Then over the pulley we'll have string on which we'll suspend about 20 grams of mass. Now the hanger here is 15 grams, and then I have the hanger is 5 grams, and then I have an additional 15 grams that'll sit on top of this to give a total of 20. Now, in the next video, I'll show how this is properly set up, and then we'll also do two runs. So this is the lab properly set up. You'll notice that I haven't attached the hanger to it or anything like that because this pulley system is very delicate, and as you can see, it doesn't take much to get it to rotate. So that said, some caveats that you should be aware of. If you were to follow the instructions explicitly and just to put the pulley on here, what would happen is that the pulley's angle would be straight in like this, but the way it pulls from this edge pulley right here would cause it to hang over and potentially derail. So the best way to do this is to line it up the edge of the pulley with the edge of this pulley, so when it unwinds straight. Okay? Now, that said, some other caveats that you should be aware of is that as this thing turns and you're exploring the moment of inertia, the pulley itself right here that has the string wound around it, that has a moment of inertia as well. And so does this cylinder that goes through. So at the end of the day, your data is going to have that information in there. Now that said, these things themselves aren't that massive, so what we will be able to do is to sort of account for their behavior in the experiment by doing a separate run that involves just the plate and the pulley system. Now here is our wheel as well, or our cylinder rather, or I don't know, hoop, thick hoop. And one thing I'd like to point out about this too is that it's not necessarily uniform. If you look at the very end, there are dimples that allow this thing to anchor into this super pulley right here, and those will add some level of moment of inertia, much like little bits of mass rotating around a central point. Now that said, you're going to end up doing two runs. One run will be the composite one, in which you take and you put the hoop on here. You want to wind this thing up to where it's almost at the pulley. We'll put our fingers here to keep it in place. So there's your object right there. And then it doesn't take, like I said, much mass to get this thing to go. So you let it go. You have an exchange of energy between this and between this, and then before it unwinds all the way, we'll stop it, and that should be data that's good enough. You can see it slipped off. It's right there at the cusp. So let me wind this around here. Oops. Too fast and hit the edge. There we go. So there we go. Now, one thing I'd also like to point out is that as this thing rotates, even though it's rotating about a central axis, you may be able to see a slight wobble to it. Okay, so that would give you an axis of rotation that's not explicitly straight. There's really not a whole lot you can do about that except for note that fact in your experiment. So there's one run with your composite object, And then you have one run with just the super pulley. And this super pulley doesn't weigh a whole lot in comparison to that, so this thing is going to zing pretty quick. So once again, you wind it up to where it's almost at the bottom of the pulley, and then you release it, and then stop it. That said, in your experiment, your spreadsheet, I will give you the interior and exterior radii of this, along with all the other pertinent information. For example, the information that we need to know about the plate, and we'll run with that. Hello, and welcome to Lab 8. Lab 8 is a lab that deals with the moment of inertia, which we know is the rotational analog of mass. So what I've drawn here is sort of a mock-up of the lab itself. If you've read the lab, you know that you have a number of runs that you have to do, some of which include a metal ring or hoop attached to a plate that acts to hold it in place, and then one in which you just have the plate itself. Now, the goal here is to try to experimentally measure the moment of inertia I of both the hoop and of the plate. To do that, we have a mass that hangs with an initial velocity of 0. You release the mass, and as it falls, what it does is to pull on this pulley and cause it to rotate. Now, the way this resists that acceleration, in this case, the angular acceleration, is going to allow us to determine what I is of this particular system right here. So if you think about it, we have a force diagram that we can draw on the mass, which is this right here, in which you have the tension in the string going up, and you have the weight of the mass going down. Now, when we release this, you're going to have net acceleration downwards like this. So this will be the direction of the acceleration. So if I were to just look at this particular system and sum up the forces, of which I have two, I have a positive tension. I'm going to have at the end of the day a negative weight, and those are going to act on this particular mass here to cause it to experience acceleration. Now, if you call this the y direction and this the x direction, in the x direction, nothing interesting is happening. In the y direction, however, we have a positive tension, a negative weight, and those are going to cause a downwards or negative acceleration. Now, this acceleration is also going to be the same tangential acceleration that the pulley on the bottom of this experiences. So this A right here is going to be the same A as this. So I'll go ahead and just call it A sub y. So let me take and rewrite this over here. Okay, now what I've done is to put in the fact that the weight of this mass is m times g. And now let's take a look at the torque. Now, we've measured the radius of this bottom pulley, so we know r. We're going to, thanks to our force diagram, connect these two things here. This is a tension that is causing this thing to unwind. All right? That tension is the same as the tension here. So from a torque standpoint, the torque here, which would be R cross F, as drawn, since this is at right angles, in magnitude is just R times T. Now, we also know that torque can be written as I times alpha, where alpha is the angular acceleration.
And we also know the relationship between angular acceleration and tangential acceleration. A tangential is equal to r times alpha. So, as drawn here, we can rewrite that as alpha is equal to a sub y over r. So, since we have this relationship between the r cross f torque and the I alpha torque, we'll put this over here. R times the tension is equal to I times alpha, and let's not forget alpha is a sub y over r. Now, using this equation, the tension in that string, which is also what's responsible for causing this to unwind and experience angular acceleration, is equal to m times g minus a sub y. Now I'm going to plug that into this. Now the goal here is to find I. So if I multiply both sides by r over a sub y, what I get is this. Whoops. And if I clean this up a little bit, I get that. Now, in this experiment, we know what the mass is that's hanging off this is. We're given that in our spreadsheet. We've also measured r, which is the radius of our pulley right here. G is just the acceleration due to gravity. A sub y is something that we're going to experimentally measure by looking at the data that we plot. So we have everything here on the right-hand side. We can calculate I and then compare the experimental I, which is what we get here, to the theoretical one, which is a combination of a thick hoop sitting on top of the disk. Now, that's it for the theory section, and I'll see you in the lab.